Dear students, today we will discuss scattering theory in quantum mechanics. Okay, you know the scattering experiments have great significance in physics. For example, most of the information about the forces and interaction in atoms and nuclei have obtained from this scattering experiment. For example, this Rutherford alpha particle scattering that you know very well. Okay, the alpha particles here, the scattering of alpha particle from nuclei has led to the nuclei atom model. Okay, then another scattering experiment, that is the high energy electron scattering from nuclei, has led to the determination of nuclei radii and charge density of nuclei. Okay, so this there are many other scattering experiments is also there. So this scattering experiments have great significance in these science section. Okay, so a typical scattering experiment consists of following arrangement. So we have some incident particles. Okay, in this typical scattering experiments, we have some incident particles, alpha particles or electrons, or here we are dealing with the quantum scattering. So here we are taking quantum particles like atomic particles. Okay. Then we have some scattering center. Okay, scattering center. So this incident particle is scattered from the scattering center. Okay, so scattering center. Sometimes it may reflected back. Okay, likewise different particles will be scattered in different angles. Okay, this is our scattering center. Okay, due to some potential, actually our incident particles are coming with some momentum, okay, which is influenced by some potential here, and it is deviated, it is scattered through some angle. That's what happening in scattering. Then we are placing some detectors. So some detectors at infinity for studying these particles. Okay. By analyzing these scattering particles, you will get the information about the interaction between the incident particles and our potential. What if it is nuclei, interaction with the nuclei with our particles. Likewise. So the typical experiments contains following arrangement, that is incident particles with some momentum. Okay, it's coming, then it is scattered by, or it is deviated due to our scattering potential. Okay, then our detector is placed at infinity. Okay, our detector is placed at infinity. These are the typical scattering experiment. Okay, then in classical scattering you have already studied in scattering particles. So here we have to study the quantum scattering. Whatever the classical scattering or scalar scattering, we you know that the two quantities. One is differential scattering cross section. Okay, differential scattering cross section. Second one is total scattering cross section. These two quantities are called the experimental quantities of scattering. We have to find out this differential scattering cross section and total scattering. We will discuss what it is actually. So we have to find out the formula for differential scattering cross section and total. That will give you by incident particles. So next session we are going to derive or we are going to see what are this differential scattering cross section and total scattering cross section. Okay, so we have to analyze our experiment scattering. Okay. We continue the scattering. Okay. It is convenient to choose. It is convenient to choose a coordinate system with the origin at the target with the center axis in the direction of incident beam. Okay. Direction of incident beam is z axis, and it is in origin we are fixing at the target. Okay, or scattering center. Then we are, since it has a spherical symmetry, we are dealing with the system in spherical polar coordinates. Okay. Here the theta is the angle. This is our scattered beam is deviated in this angle. So theta is the angle between the z axis and direction of the scattered beam. Okay. Then this is there will be phi, that you know, it's an azimuthal angle. So you have to project this this into the xy. This is z axis, so xy plane will be like this. So you have to find out phi corresponding to this theta. So we are dealing with the spherical polar coordinates. So you have to change the, suppose you are here, we have to analyze the scattered particles. For that we have to use dictators, or we have to scan dictators in different angles. So you are changing theta to some angle, so you will get the dictator here, then theta again changing theta. So if you are changing theta here in all the direction, okay, for getting the scattered particles, then in the same time you have to change the phi also. So okay, phi means azimuthal angle in our polar coordinates, spherical polar coordinates we are using. Okay. So r theta phi r is the distance we have fixed, that is we are keeping our our dictator at infinity. Okay. Then theta is the angle between the z axis and our scattered direction. Okay. Then so we have to take the spherical polar coordinates. Then especially this theta and phi are varying when you change the dictator position. Okay. In this situation we have to find out what is differential cross section, or what is total cross section of the scattering. Okay. So what is differential cross section, that we have to find out. In this thing, you know, phi changes from what, 0 to 2 pi, spherical polar coordinates. Theta changes from what, 0 to pi. Okay. Okay. So here it is good to consider, instead of theta, it is like a solid angle. Okay. So I am taking d omega as the solid angle. So we are keeping our dictator here. Okay. D omega. This is omega. You are changing d omega. For small changes, we can take d omega. Okay. We are keeping our dictator at omega. As you change the dictator in all the direction, you are changing the omega from omega. Okay. Then we know what is omega or d omega. The equation in spherical polar coordinates, you know what is d omega? It is sin theta d theta d phi. Okay. D omega is defined like this. That is the small solid angle. The small solid angle d omega is written sin theta d theta d phi. Okay. Okay. at the target. Okay. Then the number of particles. Okay. The number of particles. The number of particles scattered. Number of particles scattered per unit time. Per unit time in the solid angle. In the solid angle d omega by a scattering center is delta n. Okay, where delta n is the number of particles scattered per unit time in this small solid angle. So there are many incident particles. There are many. It is scattered by the scattering center. If you take a small d omega solid angle, then you will have delta n be the number of particles scattered per unit time in the d omega solid angle. Okay. So delta n and j is the other quantity. J that you know is the current density you have studied. So here it is equivalent to particle density. Okay, particle density. J is the incident. If J is the incident flux. Okay, flux of the particles. That is incident flux of the particles means number of incident particles crossing. Okay, number of incident particle crossing unit area per unit time. Okay, J is the incident flux of the particle. That is number of incident particles crossing unit area per unit time. That is the flux J. Then we can say this delta n, of course, delta n, that is the number of particles scattered per unit time. Whether number of particles scattering ennallathu endinokku depend cheyum. We can say it is proportional to, of course, if you change the d omega, more number of particles will be reaching. Okay, it is proportional to d omega. Okay, it is proportional to d omega. Also sure, if you are taking more number of incident particles, again number of scattered particles will be proportional to the flux of the particles. If you take more number of particles, then more particles will be scattered. Okay, so d omega, then it is proportional to J also. Okay, then I can write delta n is equal to some proportionality constant. Of course, it may depends on theta and phi because we are changing omega for scaling the indicators. Since d omega depends on the theta and phi, we can say sure this proportionality constant is also function of theta and phi. Then sigma theta phi j d omega. Okay, this proportionality is constant sigma theta phi is called differential scattering cross section. Okay, so I can write sigma theta phi equal to what? Delta n by j d omega. Okay, that is delta n by j d omega. That is number of particles scattered per unit time per scattering center per unit incident flux per unit solid angle. Okay, so number of you can define sigma theta phi. This is very important quantity. So sigma theta phi is equal to delta n by j d that means number of particles scattered, that is delta M. Per unit time, per unit scattering center, okay, per unit incident flux and per unit solid angle. So unit incident flux, unit like solid angle and d omega unit solid angle and the scattering the number of particles in differential cross section. So actually that quantity give you the interaction between the incident particles and charges, number of particles scattered. Okay, that depends on the interaction between the another quantity we have to find out is total scattering cross section. Sigma total, okay? Sigma total, okay? It is total cross section. This is sigma theta phi. Okay, so total scattering cross section will be obtained by integrating through by integrating over all directions, integrating through all directions. That is integral sigma total is equal to integral sigma theta phi, okay, d omega, okay, d omega equal to what? Sigma theta phi. D omega is defined already, that is our sin theta, d theta, d phi. Okay, d phi, there won't be any phi means azimuthal angle at the perpendicular plane of this scattering plane. Actually, scattering plane means direction of the incident particles and the plane containing the incident particles and the z axis. That is scattering plane. So, if the phi is in the perpendicular plane of this scattering plane, so there won't be any dependence on phi. Okay, so we can write by integrating this d phi, you will get in spherical polar coordinates. You can take it out as a 2 pi into sigma theta phi sin theta d. This is your total scattering. Here you can write actually sigma theta phi, that is our differential scattering cross section, can be written d sigma total divided by differential d sigma total by d omega, that d by d omega of sigma total, that's why it is called a differential scattering cross section. You have to differentiate sigma total with the omega, that is our solid angle. Now the assignment I am going to give is find out the dimension of sigma theta phi. You will get it will be the dimension of area. Okay, then you have to find out. That's why it is called scattering cross section. It is called. Okay, so find out the dimension of sigma theta phi. That is the same that I am going to give. So these two quantities, actually sigma differential cross section and total cross sections, are the two experimental quantities we have to find out in a scattering experiment. Okay, scattering experiment ഈ രണ്ട് quantity ആണ് നമുക്ക് എന്ത് കാണേണ്ടത്. അത് ഇപ്പോൾ whether it is classical scattering or quantum scattering, these are the two quantities. Now we have to check for quantum scattering what are the difference how we have to modify this situation, or can we take the particles with some momentum, or in quantum mechanics all the systems are replaced by wave function. So we have to take, in quantum scattering we have to take wave function or function of that system. Okay, then this is okay, this is some potential that you have to take. Okay, then you have to find out this wave function. It is coming from infinity, that is parallel particles. So you can assume this wave function as a plane wave. Okay, so plane wave is coming from infinity and which is influenced by a what? Some potential here. That is quantum mechanical picture of scattering. It is influenced by some potential here. Then it is what? Scattered by this potential. So it is coming like a plane wave which is in z direction. Then it is going like a what? Diverging wave. It is like spherical wave. In all the direction you may get what? You may get our particles. That means we have to find out how this wave function changes after scattering. So there is some distortion is taking place for our incident wave function. That we have to find out. Now you have to find out means this is our plane wave. So here it is like a spherical wave. So you have to represent our scattered wave as a spherical wave. That's only as in distance increases, means as you go from far from this, you know the intensity is also decreasing. That is the nature of spherical wave. Okay. Intensity probability of finding at a small area will be what will be small. So the spherical waves are the suitable wave function for representing this scattered wave. Okay, scattered wave representing the spherical wave. Quantum mechanical scattering, what we are going to deal with so you are representing our incident particle as a wave function. That incident particle is getting distorted due to the potential here. Here the potential, maybe it's a function of V of R. This is a simple function because spherical potential, Coulomb potential, these are the examples for spherical potential. So anyway, whatever the potential here can be represented by some V of R. So that our incident particles is scattered due to this potential and this wave function is will be changed. Okay. That next class we have to find out differential, how this differential scattering cross section and the total scattering cross section relates with our wave function or amplitude of the wave function. How you will get this sigma theta phi and sigma total from the wave function from the quantum mechanical treatment. Okay. So up to here I am just giving today I just gave you what a brief introduction on quantum mechanical scattering. So you watch this video and let me know if you are feeling any difficulty. Please let me know so that we can change the mode of teaching. Okay, please let me know within 1 or 2 days. I will okay, I have to change the mode of teaching so that so you should respond for first video test. Okay, then only I can continue the